Hello and welcome back. Today we start on section 4.1 on polynomial functions and models. So we'll start with the basic setup for a polynomial function. F of x is a sub n times x to the n plus a sub n minus 1. So the little subscript here is just saying which coefficient we're looking at. X to the n minus 1 power plus dot dot dot, so an ellipsis, plus a sub 1 x plus a naught. So notice these two also should fit the pattern. If we don't write an exponent, it's assumed to be a 1, and anything other than 0 raised to the 0 power is also just a 1. So here a sub I is in the set of reals, and n is in the set of whole numbers. I believe the author refers to it as non-negative integers. Non-negative integers are, in fact, the whole numbers. So any polynomial function has a domain that goes from negative infinity to infinity. If you're working with a polynomial function, your domain, we get to use the entire real number line. The range will vary depending on what function we have, though. Another property, all polynomial functions are smooth and continuous. So what we mean by smooth and continuous, no cusp, where we basically come to a point like that, sort of like if you stuck a stake into the ground and draped some tent fabric over it. No cusp, no corner, no gap, no hole. So none of these things will be here if you are graphing a polynomial function. If we have something called a power function, basically that means we're looking at a one-term polynomial. So here a is non-zero, also in the set of real numbers, and n, as usual for a polynomial, is in the set of whole numbers. If we look at power functions where a is equal to 1, then we can get a little idea about some points that we should see, some symmetry, domain and range, that kind of thing. So we'll start with f of x is x to the n. N is even. N being even means we could also think of it as n equals 2 times k. K would also be in the set of whole numbers then. So we could say then f of x is x to the 2k, since n is the same as 2k. So it's the same as saying I have x squared to the k power. Power to a power, you multiply. So there's 3 ordered pairs that we automatically know even without knowing the value of k. I know what would happen if we plug in a 0. 0 squared is 0. 0 to any power is 0. If I plug in a 1, 1 squared is 1. 1 to any power, no matter how many 1s you multiply, you're still at a 1. F of -1, if you square a -1, you get kicked over to a +1, and then again, we're looking at some number of 1s being multiplied together. Our result will always be a 1. So if we have a power function where a is 1 and n is even, those three ordered pairs automatically are on the graph. The origin, 1, 1, and -1, +1. This would be symmetric with respect to the x-axis. Y-axis, pardon me. Symmetric with respect to the y-axis. The domain, this is a polynomial function, so still negative infinity to infinity. But the range, as I start plugging in bigger and bigger numbers for x, squaring them, I get very big numbers, and they're positive. Positive number to a power, I get another positive number. We're approaching infinity. Lowest I can get, though, is 0. If I square 0, I get 0. 0 to any power is 0. If I have a negative in here, I square it, I get a positive. Positive to a power is another positive. So our range here, I can land on the 0, I can approach infinity. And like we talked about, as x approaches infinity, so bigger and bigger inputs, I get bigger and bigger outputs. Start plugging in very large in terms of absolute value negative numbers. Square them, you get very large positive values. Raise that to another power, another big value. So as x approaches negative infinity, f of x also approaches, approaches infinity. So the arrow means approaches. So next we'll look at what happens if a is 1 on the power function, but n is odd. So f of x will be x to the 2k minus 1 power. So this one, I'll let you do the proof on your own, but we are symmetric with respect to the origin. Domain, since we're looking at any kind of polynomial, negative infinity to infinity. And there's also 3 points that we automatically know. 0 to any power is 0. 1 to any power is a 1. And -1 to an even power is a +1. To an odd power is -1. So 3 more ordered pairs we know automatically. As x starts plugging in very big positive numbers, positive to any power is still positive, and we're getting bigger and bigger, so f of x is approaching infinity. But as x approaches negative infinity, take a negative, raise it to an odd power. An odd number of negatives stays negative, so now we're approaching negative infinity. So our range, because we approach both negative and positive infinity, this is going to be a range of all the real numbers, negative infinity to infinity. So next we look at the idea of real zeros and multiplicity. So for this one, we're going to look at the factored version of a polynomial. So we'll do a sub n x minus c to the n, and we'll multiply that by x minus k to the m. So c and k are in the set of real numbers, n and m are in the set of whole numbers, since those are the exponents and we want it to be a polynomial. The zeros of a function are places where the output would be a zero, so those are going to be x values. So this has zeros, x equals positive c, x equals k. Multiplicity is just saying how many times would that have been your answer. So if I expanded this out, I would have n copies of x minus c multiplied together. So our multiplicity there would be n. This one I would have multiplicity of m. Now, as far as what it does at that spot, we're going to look at a quick side example and then finish this off. If we look at the graph of f of x is, let's say, x minus 3 quantity squared. So we know this is a parabola. A is greater than 0, so it opens up. And the vertex. Take a second, see if you can figure out the vertex. Pause if you need to. Okay, so our vertex, hopefully figured out, was at 3, 0. So a quick, very rough sketch of this. So not an acceptable graph if you're asked to graph something by shifting or translations, anything like that, but just sort of a rough sketch to get another idea through. Notice that the graph basically touched the x-axis and bounced back. So if n is, we'll assume even, it will touch the x-axis at x equals c. Next we'll look at an odd function. So take a minute and do a quick sketch of this one. Pause the video if you need to. Welcome back. So this one, we have our x cubed graph. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, negative 1 quantity cubed, negative 1, negative 2 quantity cubed, negative 8. And then we shifted left 4 units. So this one had an odd multiplicity and it crossed the axis. So assuming that m was odd, it would cross. So evens bounce like a parabola would, odds will cross at that point. So then we'll talk end behavior. we have f of x is, say, 2x squared plus 50 times x minus 2. Close to the origin, all of these three terms are really sort of contributing to the overall behavior. But as we start getting farther and farther out, bigger and bigger values of x, you'll see that the main contributor to the change in the y values is going to be whichever term has the highest degree. So for example, if I want f of, we'll keep the same f of x as before. We'll keep this example going. So let's say we find f of, well, let's do 1,000,000. So 2 times 1,000,000 squared plus 50 times 1,000,000 minus 2. So f of 1,000,000 is 2 times, so 1 by 1 is 1, and then I have 3, 6, 9, 12 zeros. And here we have 1 times 5 is 5, and then we have 6, 7 zeros. And here just a minus 2. So even though the 50 million, yes, that's a relatively large number, but over here we're looking at, let's see, ones, thousands, millions, billions, trillions, 2 trillion. Totally different scale. And the farther we get from 0, the bigger the numbers are that we put in. This guy's contributions get less and less significant. These guys' contributions are just going to keep getting bigger and bigger. The gap is going to get wider. So the end behavior of this thing will behave like y equals 2x squared. So even though we don't know what else is happening with this one, we can pay attention to the power function for the end behavior. So here we have a positive leading coefficient and an even exponent. So then we know as x approaches infinity, f of x will also approach infinity. As x approaches negative infinity, f of x also, because of this being the highest power, will approach positive infinity. Approach, not equal. My apologies there. We can do a little bit of approximating with calculators. It will say approximate solutions. It'll let you know that we're estimating using a calculator. So let's look at another f of x. This time we'll do 2x cubed minus 8.4x squared plus x minus 6. So our end behavior on this one, we don't need the calculator just yet. It will act like y equals 2x to the third, positive leading coefficient, odd exponent. So this is the general shape that we'll expect to see towards the endpoints. So as x approaches positive infinity, positive cubed is positive, positive by positive stays positive. F of x will also approach infinity, but as x approaches negative infinity, negative cubed is a negative, negative by a positive is still negative. F of x will approach negative infinity. Intercepts, if they tell us to approximate them, then we're just going for the calculator. So we go into our y equals screen. Let me go ahead and change the mode. One of my other classes, I changed the mode there. All right, so here's our y1. So that's going to be our 2x raised to the third minus 8 4/10 of x squared plus x minus 6. We'll start on zoom 6 and go from there. Okay, so we can see we're missing one of our turning points there, but it does look like we only have one x-intercept, one y-intercept. Now our x-intercept, second and calculate, we're looking for the 0, and we're looking to get on either side of this guy. Incidentally, we did also just find the y-intercept as well. Add 0, -6. That should make sense based on what the polynomial function was to begin with. If you pay attention to your y values as you're going, you'll also get a sense of where to set that min, the y min, for when we adjust this thing. So left bound, right bound, and a good guess. We'll think for a moment. So x-intercept about 4.2, and since it says 4.8, we'll call it 2.5. We'll round that 4 up to a 5. This 4.3 e -12, basically that is saying the calculator's version of scientific notation. So it's a negative number, a 4, a 3, and 11 zeros in front of it before the decimal. Now, how do I know that I've got all of my turning points? How do I know that it didn't bounce back up here and then turn around, go back down, approach negative infinity? The number of turning points for any polynomial is 1 less than the degree of the polynomial. So this was a third degree polynomial, maximum of 2 turning points. There's one here. I know there has to be one down here, and we can adjust our window to see it. So maybe -30. And we'll scale those by 5s instead. And now we have a little bit better picture of where those turning points are happening. So our turning points are also, you might notice, relative extrema. So second and calculate, we're looking for a local maximum first. So here's our left bound, our right bound, and a reasonable guess. It'll think for a minute. And about 0.06, comma, -5.97, so 9698, round that to the nearest hundredth. And we have another turning point that's happening at a local min. So same idea, second calculate, local min, left bound or right bound, and a reasonable guess, let it think. So at about 2.74, -25.18. So then we can give intervals where this graph is increasing, decreasing, or constant. So increasing from negative infinity up until we hit this local max at the 600th. We decreased between the 600ths and the 27400ths. We were also increasing after the 27400ths and increasing forever. So again, if we go back to our graph, we can see that. So increasing, decrease for a while, start increasing again forever. So domain and range, we know the domain, since it's a polynomial, negative infinity to infinity, and based on the end behavior, the range is also negative infinity to infinity. All right, so from section 4.1, I would recommend 1 through 14 all, and then 15 to 105 every other odd should be just fine. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.